Last time I derived this propagator from the basically time evolution operator, the matrix element of the time evolution operator. And I wrote it as a functional integral. So curly D's. I don't know. And for some reason, I time evolved this from t to t prime instead of 0 to t. Hence, I was stuck with t double primes. And let's see. Okay. T double prime. Okay. This notation, by the way, is from Nagaosa's book. Nagaosa, maybe? Might be correct spelling. So if you're looking for this type of derivation, Altman and Simons probably has it, but also Nagaosa has a very straightforward sort of derivation of this part of the path integral. This particular formulation where I have, p, x, the time derivative of x, and it's like the matrix element of the Hamiltonian. It's called the Hamiltonian formulation of the path integral. And as you might suspect from classical mechanics, there's also a Lagrangian formulation of the path integral. And the connection is just through the usual connection between Hamiltonian and Lagrangian. So if I wanted to write a Lagrangian in three-dimensional space as a function of x, y, and z, the time derivatives, the momentum, right? Just p dot r minus the Hamiltonian in the coordinate momentum representation. And from this comes the interpretation that this matrix element is an integral over something like an action. It's many, many integrals, right? These functional integrals are like all these different integrals over all the possible momenta and all possible positions in phase space, if you will, of e to the I over h times something that looks like an action. Where these variables have a time dependence, r dot. So I'm reminding you, I guess, that I did a derivation of 1D, but also this could be generalized to higher dimensional space. And the time dependence is just the sort of time dependence that occurs in this functional integral. So the interpretation of basically quantum mechanics, or of this path integral, is just that you have an amplitude for every path, and you have to integrate over all those possible amplitudes. Whatever that path is. So it's just something like e to the I h bar times an action, which in my case is a function of x and p, I guess. Oh, I have an x dot in there too. And that weights sort of the path that should be integrated over. So in the same kind of picture where I had sort of a d plus one dimensional expansion for the transverse field Ising model, for this type of general single particle path integral, I can just imagine having, I guess, position and momentum, and time is on this axis. And so my time has been discretized into steps. So I started at t, there's t plus delta t, t plus 2 delta t, I don't know, all the way up to t prime. And I start out at some momentum and spatial coordinate. That's where my particle starts out. And then I evolve this thing through a whole bunch of discrete steps. I don't know. And in the limit where I write these functional integrals, like what I've done is I've taken all these discrete steps, so all these discrete insertions of the resolution of the identity, and I've just made this path smooth, And so that's one path through, if you will, phase space, time evolved through phase space. And what you're doing is integrating through all those possible paths. Right? So in this path integral formulation, very generally, what we've done is written quantum mechanics without the use of operators. But there's a cost associated with that. You don't really get anything for free. You have an infinite dimensional integral over all paths. So the largest contribution to this integral comes from the classical path that the particle would take, right? But then all the other amplitudes, I guess, contribute, or all the other paths contribute according to their amplitude. So there's, the question is whether or not that's, I guess, an easier approach to solving problems in quantum mechanics. It's equally fundamental. You could start with the Feynman path integral, which is basically what this is, and derive everything you need to derive about quantum mechanics. So it's equally fundamental, but it's, I guess, in terms of practical use, it has advantages and disadvantages. So the main advantage that we're going to see in this class is that this type of formulation of quantum mechanics allows you to basically solve non-interacting problems exactly through Gaussian integration, and basically develop controlled perturbative approaches to cases where you have interactions in many particle systems. And another thing that it gives you is a way to sort of represent I guess, quantum mechanics using classical computers. So you can imagine, this path, representing this path integral, and it's sort of a D. So in this case, 0 plus one-dimensional space-time. As long as you can break down, the time evolution into something that involves just real numbers. So there's one more subtlety with that, which is connected to the Lagrangian, is that in this case, if you have a kinetic energy that's quadratic in P, you can do one additional integration. Lagrangian, maybe? So the Lagrangian form of the path integral is the same object, but you've gotten rid of the functional integral over the momentum. And you're left with something like, I'll just write it like this. I'll write it generally. You're left with something that's a function of just R. I put these limits on here. And the time derivative. And the exact form of that Lagrangian you'll derive on your assignment. But when you can integrate out this P dependence, again, the thing that occurs there, it's the same as removing the Berry's phase from the problem. So in any of these cases where you have this quadratic term that lets you do the Gaussian integration. So in the cases when you can't do that integration, you're left over with a Berry's phase. And the Berry phase, it's manifest in different ways for different Hamiltonians. We'll study it in detail when we look at the spin coherent path integral. But it basically throws a wrench sort of in the sort of general formulation of these path integrals in terms of like a real, a real amplitude. And in some sense is a very fundamental manifestation of quantum mechanics. So you'll integrate out the Berry phase on your assignment, but we'll see it later in the class. It'll come back to haunt you several times. So one other thing I want to mention about these path integrals before we move on, the single particle path integral, is also the connection to statistical mechanics. So I've been throwing around the sort of terminology that this direction is imaginary time, even though it looks like I've produced it with a time evolution operator. So imaginary time comes from replacing time with I times something called tau. This is your Wick rotation. And simply substituting that into the path integral. This will produce a matrix element which looks like tau over h bar. Okay. And still the functional integrals, which are now functions of tau. I have to integrate over maybe a different tau, but that's just a subtlety. Then inside the exponential, I'll have something like, if I got all my minus signs right, I better use tau primes here. I'll just write the Hamiltonian out in terms of operators so we get the signs right. D tau prime. Okay. So that comes from basically rewriting dt as d tau at the cost of a minus I, which comes out front and affects your I over h bar. And then also, man, forgot the most important part. There's an I right here. Because your time derivative, right, gives you a transformation from x dot to I x dot. Okay, because it basically comes in like, you know, the denominator, if you will. So that leaves you with something that's, you know, real everywhere except for the Berry's phase. And that's important. That's important because if it wasn't for this complication, then you can make the identification by setting tau equals to beta h, where beta is your inverse temperature. With a partition function. I'll just write it like this. So it means, except for the complication of the Berry phase, we could write the path integral in imaginary time after this Wick rotation as a classical, you know, the expansion of the partition function in d+1 dimensions, right? Which lets us take the quantum mechanical problem in d dimensions and solve an equivalent stat-mech problem in d+1, just like we did for the transverse field Ising model, right? Exactly like we did for the transverse field Ising model. There, working with a specific Hamiltonian made it such that we don't encounter the Berry phase. We actually took that, I guess, off-diagonal operator and wrote it as an Ising coupling between different time steps, right? So in the transverse field Ising model, we had Ising couplings between time steps in the path integral. But in this case, we see generally how the Berry's phase kiboshes a strict classical interpretation.
Isn't there an extra constraint when you do the weak rotation? Like when you have this imaginary time or real time, you were summing over paths that have fixed ends.
Right.
When you do the weak rotation, then you have to identify ends of the path, right? So it's
right. So this, if you want to write the partition function, yeah, you're basically a sum of diagonal matrix elements. It means that this position in phase space has to be the same as this position in phase space. Yeah.
And a question that might not be relevant for the course at all, but so we're doing this for non-relativistic particles, in which you have this quadratic Hamiltonian. But what about if you have a relativistic particle in which it's linear in P, and you make the integration, but you don't get the Lagrangian at all, right? Yeah,
I have no idea.
Because I mean, the question is because you usually look at the literature, just people throw the path integral formulation without worrying about this kind of thing.
Right. In the relativistic sense, you mean?
Yeah.
Yeah. No. I'm the wrong guy to ask that question. I've only worked in Euclidean path integrals for these non-relativistic systems. So any QFT class, that's basically what they cover, right? It's relativistic. Yeah. But yeah, so I'm not quite sure. I've never went through the derivation of those. So this is sort of like you'll hear this called Euclidean path integrals, or like somehow associated with flat space and all this type of stuff. But I won't use that sort of lingo in this class. Okay, I think that's all I want to say about the single particle case. Berry phase. All right. Any more questions on this stuff? We'll come back to it. This is kind of the thing that's going to guide us through the many particle construction of the path integral. Okay, just a simple single particle case when I'm in momentum coordinate representation or phase space. So what we want to do now is imagine, instead of having a Hamiltonian that's, I don't know, p squared over 2m plus x squared or something like that, is we want to have a Hamiltonian that's written in second quantized form, like A dagger A, or like in assignment 2, you're going to look at the Hubbard model. Okay, so you're going to have second quantized operators for fermions there. And you can start thinking about how you construct the path integral. And there's several pieces that go into the path integral. There's this sort of imaginary time expansion, if you will, in discrete. You take discrete steps in t or tau, insert resolutions of the identity, and then take that limit of the delta t to 0, blah, blah, blah. But like we've seen twice, the important part of that, or the difficult part of that, is evaluating the matrix elements that give us, like, the thing I written is H there. And in the single particle case, we were working in a mixed, p and x basis, and because the Hamiltonian is written as p squared and x, some function of x, right? We have an eigen equation for the Hamiltonian. So the question is, how do we form an eigen equation for second quantized operators. And we need that in order to form the path integral in the same sense. So this eigenequation, or these eigenstates, are called coherent states. So it's like you're accumulating a phase, that comes out in your functional integral every time you insert this resolution of the identity. So you want to somehow absorb this phase as much as possible, which makes you want to have a set of suitably chosen eigenstates. So the question is, how do we choose these eigenstates? So they're called coherent states. And we want eigenstates, the second quantized operators. So, say A dagger, A. Okay, so we'll consider bosons and fermions separately. And our goal is to basically construct eigenstates. I don't know, I'll call them curly phi. And this is a general state in Fock space. Okay, so it's a coherent state that lives in Fock space. So quite generally, it has to have a form that's something like, you can always write it. As a superposition, or as an expansion, with expansion coefficients. In the occupation number basis. So these are expansion coefficients. And each one of these states is generated by the creation operator. And this general state in Fock space has, can have different particle numbers. So this expansion in occupation number basis has to allow for different numbers of particles. So that just gives you a very general state in Fock space. So that's it's a superposition state. And just remember that state, that occupation number representation of the wave function is just given by raising from the vacuum, N1, N2, normalized properly, and 1 factorial and 2 factorial. Number of single particle occupied states.
Roger, are these coherent states the eigenvectors of the raising and lowering operators?
I'll show you right away. So, okay, so I'll do it right now. We constructed coherent state for the annihilation operator only. So only one of them is allowed to have a coherent state, and it has to do with the fact that we have a superposition of all these different particle numbers. I think it's hard to explain, but you know, a lowering operator lowers the minimum number. It's like this superposition of particle numbers has a lower bound but not an upper bound. Okay, and so you can lower a minimum number, and you won't have an inner product that makes any sense. But yeah, okay. Well, I'm not prepared to somehow flesh this out, but only one of the two can have a coherent state, and it's because of this asymmetry, basically where you have an absolute minimum of the Fock space representation, and you know the Fock space goes to an infinite number of particles. It turns out that you can only construct a coherent state for the lowering operator, and I'll construct that coherent state. And then let's just operate on that coherent state by the raising operator, and you'll see how that comes out. So maybe it's easier to do mathematically than this sort of hand wave. Yeah, so let's do that. So if this general state, okay, so if this obeys the eigenequation for the lowering operator, then it's called a coherent state. So I'll keep my single particle label there. I'm operating on the coherent state. And so the eigenequation, so this is like the definition. This is what I'm requiring the coherent state to look like. So each one of these phi i's. Okay, so actually this holds for bosons and fermions, but let me get to that in a minute. So this equation has to hold for every label. Okay, it's not just one of them. It has to work for all of them. So that's the requirement that we need of the coherent state. And this is where bosons and fermions become very different. And let's just talk about bosons first. So in the case when we're talking about bosons, these numbers they can be any complex number. So it's a set of all basically complex numbers. So this set, I don't know. And at the end of class, we'll see what they are for fermions. But starting with bosons, the coherent state, phi, is given by E, sum over all states, sum over all states, phi of these states, and then the raising operator, that's supposed to be a dagger, looks like a T, on those states. And so this thing you're going to prove yourselves on assignment 2. And that's the best way to remember forever what it is to prove it yourself. Okay, so I'll leave that to you. You're going to prove it next week, and I'll just start using this expression for the coherent state now, and we'll just discuss some properties of it. All right. So, by the way, I don't think the proof's that difficult. It's interesting, but and again, remember, we want that because we want to construct a path integral that has sensible matrix elements in it, basically, for second quantized Hamiltonians. So that state, that phi, that coherent state, is again, is constructed to basically give you this type of eigenequation.
Are coherent states a complete set in the inverse space?
Yeah, I'll talk about it, yeah. So yeah, let's talk about some properties. They're a complete set. They're actually massively overcomplete. Okay, so they do have some, interesting properties. So let's start with some of these properties. So, first off, the adjoint. Can just be calculated from applying the adjoint of A, which is A dagger, backwards on the ket, if you will. So this will give me the eigenequation. So again, you move this inside at the cost of the adjoint. You move this inside the ket. Operate to get this eigenequation, right? And then pull out the complex conjugate. Does that make sense? Okay, so this thing's just, so it's the sum over all these single particle states, phi of those states, but you got to take the conjugate of that. Okay, it's just what you would expect, basically. So that raising operator, like you asked, is there an eigenequation that's satisfied by both raising and lowering operators? So you could ask, basically, how does that raising operator affect the state, the coherent state? So let's apply it. Let's apply it to the thing that you're going to derive, so which is A dagger. Okay, be careful with my labels here. So I want to apply A dagger I. So I'll write J here. Which is raising the coherent state up out of the vacuum. And this gives you a nice way to see what this operation does, because you have an exponential, what it looks like is that you've taken a derivative with respect to the field, right, for that ith component, and brought down the raising operator. And so that's why the operation of the raising operator on the coherent state is different than the lowering operator. So that's why you can't have basically a coherent state. You choose it, you define it for one, and it gives you this equation for the other. Question?
Are you missing phi I star in that last term in the chain of equal signs?
In the last term where?
Just the second line where you have
this one here?
yeah.
You mean where do you want the phi I star inside here? You mean?
No, it seems like you've written only bra phi, or is that wrong?
Here, you mean?
So the last term.
This term here?
Yeah, it looks like only bra phi, not bra phi I star. Or did that phi I star go somewhere that I can't see?
Yeah. You're missing the extra factor of phi I star.
Oh, here.
Right, just the eigenvalue.
Oh, here you mean?
Yeah.
Oh, yeah, sorry. Yeah, you can't see the forest for the trees. Okay, so why is this important? So this is just the derivative of the coherent state. Yeah, so I can just write it like this, right? And so that looks analogous to what's going on with x and p in the coordinate representation. Okay? So it means that when you construct the coherent state path integral with a and a dagger, you're going to have the analogous type of terms coming out of it as you did for x and p. So I don't know if that's reassuring for you, but it's reassuring for me because it means that the sort of coordinate type of representation that we just derived for the single particle will have a lot of similarities to this coherent state representation. Okay, so similarly, if you act backwards on the ket with the lowering operator, you'll get the derivative with respect to the complex component. So you can ask, what's the overlap? What's the inner product of two states? Let me call them phi prime. And keep in mind that what I'm really talking about is a whole set, right, of particle states that occurs in the Fock space. So I could even call it, some books will have a notation that looks like this to keep reminding you of that. Phi I, it's like the set of all these particle states. I'm just defining that notation, but I don't really like it. But what you'll do on your assignment is you'll prove the overlap relationship that I'm going to write just for a single particle state. Okay, and so then you got to remember that you're really dealing with this set of all these single particle states in the Fock space. Well, I can do that actually for the overlap too. So let me just work in a single particle label. So let's see if I can do this without screwing up. All right, so I'm going to work with just I. So then I'm going to calculate the overlap from the coherent state definition. And let me expand the exponential. Okay, so I'll keep that particle label, I think. Okay, it's getting cumbersome. Okay, so that's phi, so that's the scalars, and then I need the operator. So then it should be a dagger I to the n. All operating on the vacuum. Okay, so this is a general way to do proofs when I ask you to do proofs on the assignment. You can look at single particle labels first. And then, a function of operators is defined by its Taylor expansion again. So you just do the Taylor expansion. And then you apply the operators, and let me do it in a weird way. I'll do it over here. Let me break up that n factorial into the product of two square roots. Okay, so let's keep going over here. Right, so for the single particle state, I've just broken up the coherent state operator, if you will, or the definition, the generator for the coherent state, into this term plus something that gives me exactly, right, the occupation number representation for that single state, which is Ni. Okay, so you can repeat that for the ket now, or the bra, for the adjoint state. That'll give you something like okay, I'll keep my single particle state labels distinct. So I'll have two sums. Okay, I should be more careful here. So okay, so for my adjoint, so for my bra, I'll have this Ni, right, okay. And then this is my J state. Okay, I didn't really have to do this because this is just a scalar, right? So I could have written this in 0 steps, which I guess wouldn't have been all that meaningful. But so what I'm doing is I'm thinking of this scalar. I guess I'm pulling it out, but then I have, you know, orthogonal states, the inner product of which just requires that my indices are the same. So that's all it is. So I only have one n. I can throw away the I and j labels, I guess. I'm going to have the state conjugate and itself raised to the power n, right? What else? Then I'll have n factorial on the bottom. Yeah. So I can just re-exponentiate this. Okay, so you can imagine you do this for the single particle label, right? Then you can just generalize it to the many particle case. But it gives you the nice trick. This gives you the nice trick for some of these proofs you'll have to do where you have an exponential, you write it as its series expansion, right? But then this somehow relates to, you know, basically the definition of the occupation number state in Fock space. Right, so that's cool. The overcompleteness. This occurs in the overcompleteness relationship. These boards really suck. So the completeness relationship is actually really important, obviously. Okay, I have a note here. So you're going to do this you're going to prove this in your assignment 2 question 2. So take these pieces that I've given you, and you'll put this all together to prove the overcompleteness relationship. And that's this. It's a product over these labels I. This thing, which is really just the many particle, I have a minus sign. Well, it's a many particle relation to that thing. I think this is right. You tell me when you do your assignment. This is the most complicated way to write 1 in the world over Fock space. You'll just see it written as 1 all the time.
Didn't you already say that about a different way to write 1?
This is even more complicated. It just gets more complicated. This thing here, I don't even know what it is. This has to be defined. So this integration variable basically runs over the real and imaginary parts of that complex number. Okay, so you'll do that on the assignment. This thing gives you all sorts of useful properties, some of which I don't want to write down. We'll use them. You know, the trace of an operator. If you write the trace of an operator out and you want to perform that trace in coherent states, you basically just insert this resolution of the identity into that trace formula, and you'll use the completeness of the old basis to get basically a trace that is just, this thing times the matrix elements, the diagonal matrix elements of whatever you're looking at. So it has all the same behaviors of these types of objects in quantum mechanics. A general state in the space, I guess that one's relatively important. So I won't write the trace out, you'll use it at some point. I think it's simple. I mean, once you have the resolution of the identity, everything follows from that, I think. Right? You can write all your basis transformations and everything. So. I don't know, I'll just call it psi. Inserting the resolution of the identity in front of this thing. Will just give you basically the wave function written in that basis, which I'll write like this for now. And I have one more bra left over, where this thing is just defined. It's the coherent state representation of the wave function, right? So this is just something like or you could write it as, the complex of the wave function. However you want to define this notation. Okay, so all these things follow from this overcompleteness relationship. That's bosons. You'll do fun stuff with bosons in your assignment. Any questions on that? I know it just looks like a bunch of squiggles right now, but you will become experts in it. What about fermions? So fermions, the motivation for the coherent state's the same. You have an eigenvalue equation, and you want to use the eigenequation to, write all the matrix elements in your path integral or something like that. Okay. But you also know that fermions have this statistics, right? They have this anti-commutation relation. So fermion coherent states require a quite different treatment. Lots of times I just use this row thing, to write general formulas, like for raising and lowering operators that basically, is used to distinguish between bosons and fermions. Then you got to keep track of the occupation and blah, blah, blah. But for coherent states, we really want to be careful with how we, define the fermionic version. So we want to define, I'm going to use completely different notation for the coherent states. I'll use eta. So this is your phi for fermions. And, you know, a to I, oh god, it begins. This is the eigenvalue. Okay? But what is that eigenvalue? So we should keep in mind that there's an anti-commutation relation associated with, you know, the annihilation operators for two different labels. So I look back at my notes, and I think I wrote this with a rho here, right? But it's kind of weird because like the anti-commutator is the plus sign, and the rho is minus for, I don't know, man. So some people, you know, will write minus rho here or something like that. But anyway, just if you look in like Nagel and Orland or one of these books, you'll just see that this, you know, this thing's a little different here. So I'll just use this anti-commutation notation and just say we're sticking with fermions, okay? Okay, so just keep that in mind. Let me use alpha and beta for my labels. And let me apply the product of these two operators to the coherent state. And so the requirement in order for this to be a coherent state is that it satisfies this. I know this seems like I'm going slow here, but so this operator acts forward first, right? So I have A and then the eigenvalue for beta and the A to state back. Okay, cool. Now I have to commute this eigenvalue with the operator. And usually that, I mean, you don't care how that happens. I mean, they just commute right through, right? But let me be super careful here. And let me say that, you know, it's conceivable that I pick up a minus sign or a plus sign. I don't even know what it is. It's conceivable, right? Because of the anti-commutator. So you can assume it doesn't pick that up, but let's not assume that. So notice how careful I'm calling these things eigenvalues? Because they're not numbers, is what's going to come out of this thing. So I've commuted them, the eigenvalue, with the operator. And now the operator is next to the ket, right? So I have whatever sign or whatever phase or whatever I've picked up. Eta, beta, eta alpha, eta. Right, can I go any slower? So from the anti-commutator, then also I have minus, right? Minus this operator product. And you see where this is going now? So alpha operates first. I get eta alpha. I'm commuting the eigenvalue with the operator. Okay. So I'll assume I have the same sign structure, but then I pick up a minus sign. I'll write it like this: minus over plus. What have I done? A. Okay, so I have minus plus eta alpha, eta beta, eta. Okay, so that should upset you deeply because now the eigenvalues themselves have inherited the anti-commutation relation of the operators. So it means that in order to define the coherent state for the fermions, you have to have eigenvalues that anti-commute. Oh. And, you know, subsequently, if I square this operator, I basically have to get 0. Okay, alpha and beta are your particle labels. You need numbers now that have this property. And these are called Grassmann numbers. So who's heard of these before? Okay, good. I don't know how to spell Grassmann. 2 S's maybe? So you essentially have to define an entire new algebra for these types of numbers. They're nothing like regular numbers. They're not like the C numbers that we use for the boson coherent states. And it all follows from this anti-commutation relationship. So let me just spend a couple minutes talking about this algebra, just to lay down a little bit of the foundation. And we won't deal too much with Grassmann numbers in this class. We'll mostly look at the bosonic coherent state, but path integral. But you definitely should be aware of these beasts lurking out there. Okay, question?
So most of the systems that you guys study in your field, are they more bosonic or fermionic, or it's pretty much even?
It depends, I guess, what you're doing. Non-interacting Fermi systems, they're very well studied. The reason is you can basically do this path integral in the non-interacting case, even if you need Grassmann numbers, say, and do Gaussian integration and get everything out. So it's maybe not always written in terms of Grassmann numbers when you do these types of path integrals, but like the formulation we're developing, which applies to free fermions, is basically used for everything that has like band structures, all this stuff with like topological insulators, where you have band structures, but they have like, the topological invariant that connects the bands. So, I mean, this is probably the biggest field of condensed matter right now, and it's all fermionic. Okay. Then there's, if you're studying things like quantum fluids, like helium, stuff like that, or spin systems, magnetic systems, these are basically bosonic. The commutation relationship for spins is often bosonic. So, I'd say it's evenly split between fermionic and bosonic. I would say that the field's more advanced currently in terms of interacting bosonic systems than interacting fermionic systems. But in terms of free theories, I think it's pretty much the same thing. So
is that because it's easier to do interacting bosonic than interacting fermionic?
I don't know if it's easier somehow. I don't know technically why it's easier, except for this issue of the sign problem. The sign problem is this phase, something that comes out of this Berry's phase in some sense. Do you have some comment?
You don't have a Fermi surface in the case of bosons. In fermions, usually nobody knows how to incorporate a Fermi surface.
Yeah, that's fair, I guess. Yeah. Mm-hmm. Yeah. So I think it's pretty evenly split. I deal mostly with bosons. That's why I'm not going to teach you much about fermions because I don't know anything. So that's a simple answer. All right, this algebra is no fun. Let's just do it. So Grassmann algebra. I mean, like any algebra, it's specified by generators. I mean, I don't construct a lot of algebras in my spare time. But you can just imagine, okay, I guess these things as generators. And I'll explain what that means. So alpha, some index. For the amount of generators you need to span, the space that you want the algebra to be defined on and all this stuff. So what we're doing is we need to, just so you know where we're going with this, we need to be able to define functions of Grassmann numbers and a calculus in order to do the path integral. Okay, so just the bare bones about basically what the algebra looks like. So all these elements, all these generators, which the index alpha labels the element, basically you can form, you can add or subtract complex numbers to them to form different numbers in the Grassmann sense. Okay, so C's are complex numbers. So if I have all these generators, I'm also, I stay within this algebra. So I'll just call it, I don't know. So it's still an element of the algebra. So when you see a Grassmann number and you have an I in front of it, or you have some scalar in front of it, blah, 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 don't worry, everything's working out. Besides this anti-commutation nonsense, the product is associative, right? So which means, I don't know, eta I. It doesn't matter what order you multiply the Grassmann numbers in. There's a basis or a basis set for the algebra, right? So a number in the algebra is defined with this basis set. It's a set of all elements, I don't know, and their products. Alpha 1, alpha 2. Okay, so the number, a Grassmann number, is like a linear combination of all these elements in the basis set multiplied by a complex number. Okay, so linear combination with complex coefficients. That's what I would call a number, I guess, in the Grassmann sense. For lack of a better word. Right. This is like the bare bones, that I can think of. The only other thing, I mean, look in any book for the full algebra. Most condensed matter books won't even have the full algebra. They'll just be like, look in some other book, right, for the full algebra. The only other thing is that you want the concept of a conjugate, just like you have a complex conjugate for the C numbers, for the bosons. So you basically need this idea of a conjugate. And so the number of elements has to be even in order for that to work. Because you have to associate every generator with a pair. And it's not clear how you do that a priori. But in order to have any sort of conjugation, you basically have to have pairs, just like you have real numbers paired up with complex numbers, right? That's the conjugate operation for that algebra. So you need the same thing in the Grassmann algebra, which gives you a restriction on kind of these indices. And we'll have a really simple restriction on those indices. I mean, we'll just look at 2 basically. So it's the simplest way of implementing this algebra. Okay, so it's a conjugate operation. It's I don't know, I guess that means pair. So they call them conjugal visits in jail, right? They only allow 2 of you in a trailer. So you need to have 2 P. God, I forgot these are recorded. So you need a number n. So if I put a maximum here, so n. So you need to define some other integer, I guess I'll call it p. N has to be even. I could have wrote that. So n has to be even. And then the conjugation operation is just a way of specifying this pairing. So if I have an element of this, if I have a generator, and I do the conjugate operation, it defines this number, which I think in some books you'll see in the Grassmann algebra as just like a bar. And because you're associated with pairs, if you do it twice, it's just like a complex number, right? So if you do it twice, you just get the same generator back. That's a little harder here. And I think that's it. Oh yeah, that conjugate operation, because we want to define numbers that are combinations of the generators with complex numbers, we'll often be looking at the conjugate of a complex number times the Grassmann generator. And so that's set up in this algebra just to behave the way you want it to behave. Then C eta conjugate gives the complex conjugate of that C number times the conjugate of that. They're not operators. There's no adjoint. here. It's just associating a pairing of the Grassmann generators. That was it. That was pretty good. That was like 5 minutes of defining the algebra. That's all I really want to say. So for our fermions, we're going to restrict this to 2 generators. And I'll call them, there's no index then. I mean, I could call it 1 and 2, but we're just going to call it eta and its complex. Or sorry, its conjugate, or eta bar. And we're going to use that to define, the algebra. So the elements of the algebra, the set, now just has so it's generated by this basis that's just 1 eta, conjugate eta, and the product. And that's all we're going to need. And then the number, the Grassmann number, it's just any linear combination of these with complex numbers. Then some number, I don't know, A. So that's a number that's an element of the algebra. So we're going to use this, 2 generating function Grassmann algebra to define functions. And also to define the elements of a calculus, I guess. So maybe I'll continue with this next time. The functions, maybe I won't even talk too much about defining functions. Functions of these Grassmann numbers are just going to be defined in the same spirit as you define functions of operators. They're defined through their Taylor expansions, say. So that one's not actually that hard. But the calculus is really fun. So I don't know, we'll use it a bit, but I just really want to look at the calculus. So we'll spend like a few minutes defining the calculus next time. And then we're going to go on and start creating the actual path integrals, okay? We'll go back to bosons, and we'll look at the coherent state path integral in all of its glory. So that'll be on Tuesday. Any questions?
Yeah.
Question? N is, yeah, I'm just saying there's an even number of indices here. Yeah, I wrote N after. I went back to this board and wrote N. Yeah, it's a complicated way of saying even.
So just 2 things. One, what are the commutation relations between the conjugate and the non-conjugate? Are they similar to A?
Yeah, we'll go through them. Yeah. It's worth doing that and maybe in some detail. But
Can we have some generator that is self-dual?
a generated self-dual?
Yeah, self-conjugate.
Self-conjugate. I think it's just one generator then. Although, yeah, like unity, right? Like.
You can prove that it has to be a single number.
No, I personally can't. No, that's a good question. Yeah. No, I'm not sure about that. I haven't looked too deeply into the algebra. Like a physicist, I just use it, right? Oh. Grassmann numbers are fun. They're fun until you really need to do something with them. I don't know. Yeah. Okay, so we'll continue the fun next time. Bring your assignments. Email me your assignments. And I'll have another assignment for you on Tuesday.